So we started discussing a harmonic oscillator. Basically, you can create a harmonic oscillator out of any system, right? You have a system. If you plot potential energy, find any stable equilibrium point, basically a minimum point in that potential energy function, right? And create a small displacement, and voila, you will get a harmonic oscillator. Small oscillations of a single particle around a stable equilibrium point. That's what harmonic oscillator is, right? And then we spent like the end of the previous class discussing how we can model that restoring force which drives a harmonic oscillator, right? So, of course, we just expanded a potential energy around that stable equilibrium point, whatever stable equilibrium point you pick, and naturally, out of that expansion, Taylor expansion, we got the expression, not the expression, basically the formula, right, for potential energy. So 1 over 2 kx squared, right, where k we no longer call it spring constant. Spring constant, it's a property of or intrinsic parameter of a spring. In this case, we can create oscillations of any system, and that k can be of any nature, right? So we usually just call it a force constant, right? And since, again, we all know that oscillations can be only around stable equilibrium points, so that that force constant, must be positive, right, in order to have oscillations, right, in order to be around a stable equilibrium point. If k is negative, basically it means that because k is basically second derivative of the potential energy function. Negative second derivative, it means that you are at the unstable equilibrium point, at the maximum, right, and any displacement in your and the force will just drive the system away from the equilibrium point. So every time k must be positive to be around the stable equilibrium point. So as I said, we spend the whole time figuring out how we can model that restoring force, right? And we can model it in the form of a potential energy, 1 over 2 kx squared, which is called Hooke's law. Or you can make a transition to the expression of a force, right? We've done it. And of course, we ended up with the force equals minus kx, which is also called Hooke's law. So basically, we derived, right? So now, once we know how we can describe that restoring force acting on the particle, right, to have a harmonic oscillator. So now what's next? We need to describe that motion. So how can we do it? Newton's second law, universal law, we have the force. And so today we will just start solving that differential equation. Start solving Newton's second law, second order differential equation. All right, so we discussed what we've done in the previous class, and now, before we start solving, let's look at the example, all right? And the example which we discussed, a few classes ago when we had a cylindrical surface, right? And you remember we had the cube oscillating around the top, right? So let's see, can we get a harmonic oscillator, Hooke's law, out of that potential energy, because we claim a general validity of the Hooke's law. So any system, you can, if you find stable equilibrium point, you can create a harmonic oscillator. Can we get a harmonic oscillator out of that system? Right? And can we get the same conditions for stable? So that was example. Okay, so this is example 5.1. All right, so that a cube on a cylindrical surface. It's that example, related to that example. Right. Okay, and we derived the expression for the potential energy. Of course, I don't remember. I need to look. So we derived this. U as a function of theta equals, okay, I will just grab my notes, mg, then r plus b cosine theta plus r theta sine of theta. Okay, so that was our function. We derived carefully, right? And now, so we need to, and of course, around, right? So we want to create a harmonic oscillator around theta equals 0, right? So about theta equals 0, that point, this is the point which we discussed in that example, right? So expand it. So Taylor expansion around theta equals 0. We know expansion of cosine, sine. So let's do it. Expand it. All right, so as a result, we'll get u as a function of theta approximately. Right. mg r plus b. Cosine it will be 1 minus theta squared over 2. Okay, and then plus blah, blah, blah. And expansion of sine, it's sine of theta is theta. Of course, theta is in radians, right? Plus r theta squared, right? So close the bracket. Okay, let's open it up quickly. So it will be this mg and r plus b times 1 constant. You know what can be done with the constant in the expression for the potential energy. We can dump it. We can redefine the reference level, for example, right? So constant, so can be dropped, right? And so what? Now let me, mg is the same for this term and that term, so I can take mg outside. Then let me take this 1 over 2 outside also, and as a result, what will be left inside? Theta squared also will be outside. I will write theta squared as the last one. So here 2r, because I took 1 over 2 outside, so it will be 2r, and then minus r plus b, minus r plus b, and theta squared. Right? I think I didn't make a mistake. So that we can forget about that constant, and as a result, we have 1 over 2 mg. This will be r minus b, theta squared. So that's our potential energy, right? Okay, expansion around theta equals 0. And now let's see under which conditions it is stable and what is a k, that force constant. You remember in the Hooke's law, of course, it's a 1 over 2 k x squared, right? So that was our Hooke's law. X is displacement from the equilibrium, right? So in this case, instead of x theta, and our k is mg r minus b, right? So now k, it's a mg r minus b. So our force constant. So for different systems, k can be different, right? It depends on the system, right? So in this case, it's mg r minus b, right? And so now we know what should be. We know that k must be positive for a system to be stable, right? So in that case, the system is around stable equilibrium point minimum, right? And of course, if k is negative, then of course system is going to be unstable, because in that case, system is will be around maximum point or unstable equilibrium, right? So which way I wrote it, just okay. I will write like this. So so when k is positive and r is larger than b, right? So it means the radius of the cylindrical surface is larger than the half a size of the cube. In that case, the system is stable when k equals 0. K is larger than 0. R is larger than B. Then the system is stable. And we ended up with the same conclusion analyzing that potential energy right in that example. So when the size of the cylinder larger than the size of the cube, the system is stable. It will oscillate right indefinitely. And that's what we got here using slightly different approach, right? And of course now, when k is negative and r is less than b, of course, then the system is unstable. So the same results. It's good to confirm those results using different approach. Okay, so again, general validity of the Hooke's law. Right? Potential energy, find any minimum point, stable equilibrium point, small displacements, and you can use Hooke's law to describe oscillations of that harmonic oscillator. Every time you can model it using this parabolic function. Right. Okay, so and now after this example, yeah, we will write down Newton's second law in order to have a complete description of harmonic oscillator motion. Okay, let me check if I mentioned everything. Yeah, this is done. Yeah, okay, so now, okay, I'll move probably to this side. I don't know how to title it. The book just says simple harmonic motion. Okay, why not? Still cannot come up with anything better. Simple harmonic motion. But we just basically, we're going to solve differential equation, right, to describe this type of motions. Okay, let me use just a spring mass system. But again, it doesn't mean that our solutions and all these discussions will be limited to the spring mass system. No way, right? So general validity of Hooke's law system can be any, right? But in order to, because next we will start making a system more and more complicated, we will start adding damping forces and then driving forces. It's good to have some particular example, some particular picture, right? So I will use just a mass spring system. But again, it doesn't mean that we will be restricted to that system. All right, so let's say this is our spring, some cart, right? Equilibrium somewhere. Okay, let me introduce, of course, coordinate system. X, let's say this is x equals 0, so that's equilibrium. And of course, force acts this way, right? So restoring force, F equals minus kx, right? Of course, when you write, every time when you write differential equation, that Newton's second law, acceleration x double dot, every time assumed to be positive, right? When you write it down. Okay, so m, okay, yeah, mass, m, right, x double dot, one-dimensional system, equals to the net force acting on the system. Of course, in this case, only one force. But again, when we start making system more and more complicated, of course, we will start adding additional forces to the right side of the equation. So mx double dot equals to minus kx, right? Of course, it's better to to get rid of the factor in front of the second derivative. So we will end up x double dot, of course, minus k over mx. And of course, who wants to drag these constants k over m, which are basically intrinsic properties of the system. So it's better to introduce a new constant, which will be also an intrinsic property of that particular system. Angular frequency, omega. So let's introduce. So let's denote omega equals to square root of k over m, right? So angular frequency so it's an intrinsic property of the system, right? Because it depends on the intrinsic properties. Okay, of course, this must be framed. Right. And so now as a result, differential equation, which you're all familiar with, right, equals to, you know what, probably I'll move to that side. Let me just check which way I wrote it down. It doesn't matter, right? Okay. Minus omega squared x, right? Okay, yeah, it's worth of framing because this is differential equation which needs to be solved. And first of all, let's characterize it. Let's call it names, right? All those insulting names which can be used. First of all, second order differential equation. Second order sounds like second best, right? Second order because the highest derivative is the second. It's clear. Right? Then, linear. What does it mean, linear differential equation? Linear means if you have, let's say, two solutions of this differential equation, right? Two solutions of this differential equation. And if you create a linear combination of these two solutions, that linear combination will be also a solution of this equation. So that's what linear means in this case. So it's a second order linear differential equation. Then what else? Okay, maybe I will start writing, right? Second order linear. Then what else? Homogeneous. What does a homogeneous mean? It means that since there are no any terms free from x's. So each term in the equation has its own x agent, like a KGB agent, right, controlling, right? So no free terms. Everyone is under control. X agents everywhere, right? And then when we start making systems more complicated, first we will have x dot, and again there will be term with x dot, again x agent, and then when we start adding driving force, only there free terms will appear. But this is still homogeneous differential equation because there are no free terms. So second order linear, homogeneous. Homogeneous. Okay, let me write differential equation, and I will write with what also important characteristic of this equation, coefficients next to all these x agents are constant. 1 omega squared, so it's a differential equation with constant coefficients. So with constant coefficients. So that's the full characterization. Second order, linear, homogeneous differential equation with constant coefficients. Okay, so, all right, so now we characterized it, right? And so what's next? Now let's start solving it. Of course, you know the solution, right? And there are two ways of solving this differential equation. We're going to use classical. The second one is less classical when you multiply both sides by x dot and then integrate it, right? So I used to solve that. I used to also solve this equation using that method, and then after a few years, I decided it's not worth. So we're going to use classical method. We can say, let's search for a solution in this form. Nothing wrong with that phrase, as long as you can find solutions. Maybe you can use some crazy function, and you can say, I want to find my solution in the form of these functions, but you will never be able to find these solutions right in that form. But anyway, you can try. So we're going to use the best function. Nothing is better than exponential function in terms of differentiation, integration, right? It's the most amazing function. So let's search for a solution in that form, in the form of the exponential function, right? So I will write search for a solution, right? Again, you could have said, okay, I want to search in the solution in the form of sine or cosine, right? Yeah, go ahead. Right? But it's easier to start with the exponential. Search for a solution in the form, right? So x equals e to the power of lambda t. And of course, it makes sense to search in that form because it doesn't matter what you do, that function stays. As a result, time dependence will disappear, right? Okay, so let's plug it. And of course, we will get lambda squared e to the power of lambda t, right? Okay, let me move to this side. Right. It doesn't matter. So minus omega squared e to the power of lambda t. So e exponential function gets cancelled, right? And as a result, we're getting what is called characteristic equation, right? Characteristic equation. Yeah, probably I will move still to the same side. Right? Lambda squared plus omega squared equals to 0. So it's a characteristic equation. It means that we're going to impose some limitations, and only with those limitations, this function can be a solution of that differential equation. So limitations on lambda. Right. So lambda must be equal to plus minus I omega. Only with these two. Okay, let me write lambda 1 and 2. So only with those lambdas, this function can be a solution, right? So as a result, we have, two solutions, e to the power plus minus I omega t. So we have two particular solutions. Right. Okay, so if we have two particular solutions, and they're obviously linearly independent, you will never be able to construct e to the power of minus I omega t from I omega t. All right, so if you have two particular linearly independent solutions and you have second order differential equation, then according to the theory of differential equations, if you construct a linear combination of these two particular solutions, that will be a general solution of your differential equation. And we have two linearly independent particular solutions. Let's construct a general, let's construct a linear combination, right? And that will be a general solution of the second order differential equation, right? So as a result, x as a function of t will be equal c1 e to the power plus I omega t plus c2 e to the power of I minus I omega t. So general solution of the differential equation, right? So right. Okay, let me frame it. And I will put, where should I put? Over here. Let me put row number 1. Okay, there's some shadow. Let me. Number 1. It's a first form of the solution. We are going to present 3 forms of the solution of this differential equation. It's the first one form, right? And all right, so advantages and disadvantages. Right. So x is real, right? X is real. Because what is x? It's just a displacement from the equilibrium. It cannot be complex or anything, right? X, just a displacement, right? So here, right? So that is our X. So E exponential functions are obviously complex, right? And as a result, since here we have a real, right? Real, so it means that C1 and C2 must be complex. So that product of these two complex things give us a real, right? So advantage of this solution, nothing is better than working with exponential functions. Disadvantage that you have to deal with complex constants, right? So let me write. So e to the power of plus minus I omega t, that's a big smiley face, but C1 and C2 complex, of course, that's a disadvantage, right? C1, C2 complex, and of course, disadvantage. Right. So if we have some disadvantages, let's try to change. Maybe we can get something better, or maybe we'll never get back. We'll never get anything which is better than this, right? But anyway, so let's get the second form of the solution, right? So this is the first, and now the second. And of course, we can use Euler formula, right? We can expand it, right? So x, okay, maybe let me write. So the second form of the solution. So let's try to get, that was the first form of the solution. Now let's get the second one. So x as a function of t equals, of course, C1 cosine omega t plus I sine omega t, and then C2, the same, right? Plus C2 cosine omega t minus I sine omega t, right? Okay, so we can combine terms which have cosines and sines, and of course we will end up with so C1 plus C2 cosine omega t, and then plus I C1 minus C2 sine omega t. Okay, so now we can redefine constants. So we can call this as, I think I used B. Let me check which constant I used in my notes. I think B. Yeah, B1 and B2. So that is B1, and that it will be my B2. And as a result, I can move to this side and write the second form of the solution, which is usually used as the definition of the simple harmonic motion. Right? So this form of the solution, which I'm about to write, definition of the simple harmonic motion. Oops. So as a result, x as a function of t equals b1 cosine omega t plus b2 sine omega t. So that will be our second form of the general solution. All right, so again, we can frame it. And that will be number 2, the second form of general solution. Again, advantages, disadvantages. Again, x is real, right? And sine and cosines also real. Sine and cosine, again, not much to complain, but of course it's less pleasant to work than with an exponential function, right? So we still not bad, but not as great as exponential. And b1 and b2 now are real, which is good. So now B, okay, I don't know why I use blue. No. So B1 and B2 are real, right? And okay, I can say it's a good, right? It's a good fact. I can put a smiley face, right? And then of course, sine and cosine, it's good. Maybe slightly. Small smile. Less pleasant than the exponential function, but still not bad at all. Okay, so that's the second form, and now the last one. Actually, there are 4 forms, but at some point I stopped discussing the form number 4. So the last one is called phase-shifted cosine solution. Okay, I will probably first derive it, get it, and then I will call it. I will put now a new bullet, small bullet. Right. And now out of this solution, I can get the last one, x as a function of t equals. I'm going to do this. I'm going to take square root of b1 squared plus b2 squared factored out, and what will be inside? B1 divided by this square root times cosine. Right? So if you multiply it, you will get exactly the same. So far there is no crime. Plus b2 divided by square root of b1 squared plus b2 squared, right? And again, sine omega t, right? So, okay, so now it's time to introduce new constants. Of course, the first one, this a. So let's introduce a, square root of b1 squared plus b2 squared, right? And now this construction, let me call it cosine of delta. Delta will be second constant. And I still, okay, I will justify in a second, I can call this as sine delta. How come that I can do that? You know the square of sine and square of cosine. Okay, square of cosine and square of sine, if you add them up, you're supposed to get 1. And if you take square of this plus square of that, you will get 1. Yeah, so it's legal. We can call this construction as cosine of constant, new constant, and that construction as sine, right? So as a result, we're getting okay, I don't want to rewrite it, just cosine, cosine plus sine, sine. It's a cosine of, okay, it doesn't matter, delta minus omega t or omega t minus delta, because cosine is an even function, so we can flip terms inside, right? So as a result, I can write x over t equals a cosine omega t minus delta. So that is the third form of the solution, which is called a phase-shifted cosine solution. Let me frame it. Most of the time we're going to use this because it looks small, compact, right? So this is number 3, and I will write, so it's a phase-shifted cosine solution, right? So, number 1, first form, second, and the third form. Okay, so let me check if I mentioned. Yeah, of course, A is the amplitude and delta is the initial phase. Right. Okay, let me say that, of course. A is amplitude and delta is initial phase. Right. Let me check what else I missed. No, it looks like good. And again, advantage of this that it has the simplest form, right? In terms of writing. Okay, you know what? Let me compare it with just cosine function. Right? So let me just plot quickly. So let's say I have something like this. So let's say this is t, right? And first I will plot what? Cosine, and then so that's, let's say, cosine, right? And what if I plot our function? If I plot our function, then it is going to reach maximum not over here, but it will be shifted. It will be shifted by what? This is time, right? So this will be delta over omega. Delta over omega. So at this point, it will reach the maximum only. So this function lags behind our cosine function by delta over omega. Right? So it will be right. So this is our, okay, let me use. So it's a cosine omega t minus delta, and I will write, so it lags behind, again, lags behind in time, not in phase, in time. So this lags behind by what? T equals delta over omega. Right. Then, yeah, so now we have this intrinsic property of the system. Force constant divided by m and the square root. Now, how can this intrinsic property is related to a period, to the period of oscillations? Let's connect them. So I will put a new bullet and let me write connect omega and period tau, which is period. So it's a periodic function. Of course, we can introduce period. Right? So periodic, it means that if I take, if I look at the system at t plus tau shifted by the period from a certain moment of time, actually t is arbitrary moment of time, of course it must be equal to x at moment of time t, periodic. After period, the system reproduces itself. Right, so now, okay, I will forget about delta. It's not going to change anything, right? So I'll just play with omega t. So it will be a cosine omega, let me use square bracket, omega t plus tau, right, equals to a cosine omega t. Okay, that's ugly omega. And I also know that we also know cosine function is a periodic function. So let me add 2 pi to the phase, all right? So I can write it also a cosine omega t plus 2 pi, right? Periodic, so I can do that. And now let me compare these ends, right? So in order for this to be correct, omega times tau must be equal to 2 pi. Right? So omega tau equals to 2 pi. As a result, I can write that period equals to 2 pi divided by omega. So that's how these two parameters of the system, that's how they are related. Right? And of course, we can introduce, of course, the frequency f, f, right? Which, okay, let me write first also in terms of k and omega. Right? So it will be 2 pi omega over k. I mean m over k. Right? Yeah, m went upstairs here. And of course, the frequency is reciprocal of a period. Of course, it will be omega over 2 pi. And of course, omega equals 2 pi f. Right. Since we're going to, of course, deal with them often. Okay, so we related this intrinsic constant with the period and frequency. Then, as I said, I used to solve this differential equation using a slightly different approach. You just multiply both sides by x dot, and then integration is not that bad. But it's just nice to practice calculus. Right. Although I think this approach, this solution is probably the most elegant solution. Okay, so now we have solutions. Let's look at the example. An example is a bottle. I didn't prepare a bottle. Yeah, I do have here a bottle. Bottle submerged in water in a large bucket. And so we need to, and we only know that in the equilibrium, the bottle is submerged by a distance d naught, d sub 0 given, right? We need to find the frequency of these oscillations. Right. Of course, it's going to oscillate, and we need to find the frequency. I'm thinking what can be erased. Logically, it's better to move from left to the right. Right. Probably I will do, but this is more recent. But I'm sure that you're following me. Yeah, I will erase this part. Okay, if you don't have any objections, I will start erasing. Okay, I'll probably erase up to this line and then. So, example, a bottle in a bucket. So we have bottle in a large bucket. All right. Okay. I will just draw the picture and show what is given. Okay, so I will draw two pictures, two buckets here and there. Well, I also juxtapose them. Okay, I'm just trying to estimate the amount of space I need. First bucket, and here there will be the second one. Slightly, one is slightly thinner, but okay. It kind of bugs me. Right. Okay. And, all right, so this is bottle in equilibrium, and here bottle will be displaced from the equilibrium. So equilibrium, and we're going to measure position of the bottle using the bottom of the bottle. So in equilibrium, let me position the bottom is over here, let's assume. Yeah. And then bottle goes up. And then okay, equilibrium. And let's assume that water level is somewhere here. And of course, you can put maybe some sand so that it would be in an upright position. So you can design it, right? So not a big deal. So that is water. And yeah, what is given, as I said, this distance is given in the equilibrium, right? So let me write. So this is equilibrium, okay. Right, and this displaced from the equilibrium. So this distance is given d sub 0, nothing else. Okay, and now let's displace from the equilibrium. So this will be level of water, this equilibrium, right? And so we push the bottle down. So now the bottom will be over here somewhere. Right. And the bottle itself will be so now displaced from the equilibrium. Okay. Now, of course, we need to introduce coordinate system. You know what? Before I introduce coordinate system, okay, so now this is my level of water, and I'm ready to hear listen your complaints or screaming or whatever. Any troubles with what I draw or drew, right? Or maybe you see why I drew it this way. Look, over here and over there, level of water is the same. How come? And the answer is very simple, right? Large bucket. Basically, from a mathematical point of view, large bucket, it means an ocean. Right? So bottle basically oscillates in the ocean, right? And the fact that it will displace some water, right, more or less, right, it is not going to change significantly the level of water. So that's why I usually lazy to write, but I wrote on purpose large to emphasize, because that explains why level of water here and there are the same. Right? Let me underline this, so large. So basically it's ocean, right? Okay, and now coordinate system and the rest. Okay, this is equilibrium level. All right, so equilibrium level, right? Here it means equilibrium, just a picture describing the bottle being in equilibrium, but this is the equilibrium level. And so coordinate system. X. This is x equals 0, and this will be the current position of the bottle. Again, we measure, we define position of the bottle using bottle's bottom of the bottle. Okay, so we will also need, this distance, right? So let me extend this dash line. So this distance is going to be d naught over here plus x. So this distance d naught plus x. Okay, so you will see at some point we will need it. Okay, then the last part, since we're using Newtonian approach, Newtonian formalism, of course, forces must be on the picture. In equilibrium, right, so we have two forces, force of gravity and buoyance force. Buoyance force equals to the weight of the displaced water. Right? In the equilibrium, force of gravity, of course, will be equal to buoyance force, Fb. In this case, they're equal, right? So in this case, Fb equals to mg in the equilibrium, right? But in this case, of course, buoyance force is going to be larger. So mg and the buoyance force. So now all the preliminary steps are done. Diagram is here. It looks like everything. I think I didn't forget anything in terms of picture. Yep. So now Newton's second law. Okay, it's time to get to this territory. So now, of course, Newton's second law. So mx double dot, and again, every time we assume acceleration, like treat it as being positive, right? And then force of gravity in the positive direction, Buoyant's force in the negative direction. So it will be mg minus Buoyant's force. Okay, so now let's explicitly write what is inside of this Buoyant's force. Fb equals. So it's basically, again, as I said, it's the weight of it's a weight of the displaced water, displaced by the bottle, right? So it's a mass of the displaced water times g. Mass of the displaced water is basically water displaced by the volume of this part of the bottle. Okay, so it's not given, but let's assume that the cross-sectional area of the bottle is A. In order to make a smooth transition through the solution, so we need to introduce that constant, which will, of course, naturally disappear at the end. So mass of the water, of course, it's a density of water times the volume of the bottle, which is submerged. Right, so that volume is cross-sectional area times height, and the height is d, which is d naught plus x. Right. You know what? Let me use, no, I don't want to use this bracket. I will use bracket only here for d naught plus x. Wait. D sub 0 plus x, right? And so volume, density, and times g. So that's the Buoyant's force. It looks like I haven't forgotten anything, so let me check. Of course. Okay, so let's plug it in the differential equation. Mx double dot equals to mg minus rho g a and d sub 0 plus x. Okay, differential equation. It looks like we can start solving it. But we have to make small manipulations, or maybe not so small. Let me ask you this even before I start massaging this differential equation. Okay, I will probably stand here. What's the major difference, kind of even I would say technical difference, between this system, and this system? What's the major technical difference? Actually, not technical, right? Yeah, because the nature is different, right? Okay, maybe you can see, right? Because right now we are at the point where we have to use that. So what's the major difference between this system and that system? In terms of force. Here.
The force are in the same dimension?
3-dimension, not exactly. Okay, we can, as I said, we can mechanically design it properly so it would oscillate, right? Both of them one-dimensional, right? The major difference.
That's what I said, like mg and buoyant force and the restoring force. In the spring example, you have mg that's 90 degrees to the restoring force.
Very close. But I would frame it in a slightly different way. You're sort of, what's the expression? You're barking at the right tree. Usually it's the wrong tree, but you're at the right tree, right? Okay, the major difference. Here, the restoring force, we have only one force which works as a restoring force. If an object on that side, it tries to bring it back. If at this side, the same force brings it back. In this case, we have two forces collaborating, giving us sort of like a net restoring force. So mg tries to drag it down. Buoyant's force every time works in the opposite direction. So in this case, we have collaboration of two forces. That's the major. I wanted to say it like a technical difference, right? Of course, lots of technical differences, right? So, but in my opinion, that's the major difference from physical point of view. Here we have one force, which works as the restoring force. Here we have two forces. And as a result, when we write the equation for that system, at the equilibrium, when the object is at the equilibrium, the force is zero. It's just not there at the equilibrium. But when the system is over here at the equilibrium, forces are not zero. We have mg not zero, Buoyant's force not zero. So as a result, every time when you write the differential equation at this point, every time you need to look carefully and cancel two terms. Every time there will be two terms which must be cancelled, because basically those are forces when the object is at equilibrium. In this case, it's a mg and this construction with the constant. So we need to look carefully at the equilibrium and remove those terms. So every time at this point, if you have two forces working as a together as a restoring force, you need to look carefully and remove those terms. But you don't have to. But we didn't have to do it over here because restoring force was zero at the equilibrium. Right? Okay. So I wanted to mention about that. So now. Right, so look at the equilibrium to remove, okay, let me write just two terms. To remove two terms. Okay, so at the equilibrium, we know the Buoyant's force equals to the gravitational force, right? So, all right, so equilibrium mg equals to the Buoyant's force. Buoyant's force, now, of course, we will need to use the volume of this volume of the bottle, right? So it will be density of water, then volume, cross-sectional area A, height d naught, right? So rho times volume and now times g, right? Because it's a mass of the weight of the displaced water, right? And as a result, we can use it here, right? And as a result, so this mg and this rho a g d naught, these two terms cancel each other, right? So in these cases, every time, cancel terms which are equal. And so as a result, the differential equation will look, probably I will move immediately mass to that side. So we will have x double dot equals to rho w a g divided by m and x. So, bunch of constants which are not given. It means that probably we should be able to hide them somehow. Again, let's look at this equilibrium. So, rho a g, rho w a g, and then we can also take mass to that side. It will be equal to so this d naught goes to there, so it will be g over d naught, right? So from the equilibrium, we're getting that all these ugly constants can be replaced with just g divided by the constant which is given in the problem, right? Let me check if I got that constant right. Yeah. So as a result, we have x double dot equals to g over d sub 0 x. Okay, it's time to get out of this corner. Difficult to write Okay, so we got differential equation. Something is finicky. Minus. Now I'm looking, damn it, I'm not getting simple harmonic motion. This minus, right? So it goes to that to here, right? I was describing how to cancel, and I forgot about that minus. It now. Right. Okay, now much better. So we're getting this. So as a result, equals to minus omega squared x. So where omega is square root of g over d sub 0. And of course you can get period. You can get period, which is 2 pi divided by omega. You can get frequency, right? So you can get whatever you want. Okay, it's enough about this example. And I remember once when Dr. Steinmetz was still in the department, in one of the qualifier exam, oral, he was bugging his several students about the problem like this, right? So students had to describe this system, solve it, look at some special situations, special cases, right? So now we know how to describe simple harmonic motion, which doesn't have any additional forces. Before we start making system more and more complicated, okay, I should have stepped away. Let's look at energies quickly, right? Let's write down kinetic energy, potential energy, because now we have all these solutions, so we can write explicit forms of the energies, right? Of course, you remember them, but we need to write it down. And after that, probably next class, we will start adding damping forces. So we will spend some time describing that system in the presence of resistive or damping forces. And then next step, we will add driving forces. Right? Okay, so I guess I can erase this. So like a small digression. Let's write down kinetic and potential energy and total mechanical energy for an harmonic oscillator before we start adding damping forces. Right, so now energies. Right. So now we have 3 forms of the solution, right? But of course, most of the time we're going to use that phase-shifted cosine solution. So, okay, maybe I can write of simple harmonic oscillator. So, solution A cosine omega t minus delta, right? And so let's start probably with which one I started. Potential, why not? Again, we can model it using this parabolic expression, right? So of course it will be 1 over 2 k a squared and cosine squared omega t minus delta. So it's a periodic function, of course never becomes 0, or never becomes negative. So it oscillates between 0 and 1 over 2 k a squared, periodic, right? And then kinetic energy. Let's write kinetic energy. Right? So x dot, of course, it will be equal to minus a omega sine omega t minus delta. And so now we can write kinetic energy. Again, k or t, here we use t. kinetic energy T equals 1 over 2 mx dot squared. So it will be, of course, 1 over 2 m a squared omega squared and sine to the power of 2 of omega minus delta. Okay, omega, k over m. All right. So this is k over m, whatever k for your system, for a, but for whatever system you have. So m gets cancelled, right? M gets cancelled, and as a result, kinetic energy equals to 1 over 2 ka squared sine squared omega t minus delta. So both kinetic and potential energies oscillates between 0 and 1 over 2 ka squared out of phase. Again, never negative, right? And out of phase. So let me write T U out of phase, out of phase, right? And of course oscillates between 0 and 1 over 2 ka squared. Yeah, total mechanical energy, of course. Let's just quickly write. Of course, then total mechanical energy, which is T plus U, obviously it will be 1 over 2 ka squared. Right. Okay, let's add some colors. Right. Okay, so just quick digression, and we still have a few minutes. At least we can start introducing. Okay, let me check if I. Yeah, of course, constant. Of course, it is equal to constant for a system. Right. Okay, so now let's start adding damping resistive forces. So damped oscillations. Okay, I will start erasing this. And so damped oscillations so basically this chapter consists of several parts. First, in the previous class, we model this restoring force. So introduce Hooke's law naturally, we derived it, right? So then we solved a motion of harmonic oscillator without damping forces. Now we're going to add damped forces, right? And then driving forces. We will add driving forces. Right. Okay, in chapter 2, which I never covered, usually every time I skip it, right? Chapter 2 discusses these damped forces, resistive forces, damping forces. And of course, there are two types of called drag forces. There are two. There are two types of damping forces. If a system moves with a small velocity, reasonably small velocity, then the force is proportional to the first power of the velocity. The second lecture. My voice is giving up. So, good. So if velocity is small, then a drag force is proportional to the first power of the velocity. If if velocity is large, then of course the force is proportional to the second power of the velocity, right? And so we're going to assume that the harmonic oscillator moves with a small velocity. As a result, we can use drag force, which is proportional to the first power of the speed. Right. So now we will have. Okay, probably I will draw the picture first. Again, so. So object, right? So here somewhere we have an equilibrium, right? So equilibrium, x equals to 0, this is x. And again, velocity and acceleration, okay, let me use this. So v, so x dot that way, and of course x double dot. And of course, so the spring force is a restoring force. So it will be this way. So F, which way I labeled? I think I sub R, restoring, yeah. So minus K, yeah. Need to reduce the size, Kx. And now we're going to add a drag force. Resistive force. Every time resistive force is opposite to the direction of velocity. I assume every time all these velocities, accelerations, positive, right? It's still general situation. We're not losing generality. And F, I think I use subscript D. Yeah. Fd equals to minus B times V. V is the speed, B is the constant, which we will soon change. All right. So now we have two forces. So let's add, which way I wrote it? A damping force. So F D equals to minus B V, right, which is x dot. Okay, so now we can write differential equation. So mx double dot equals to restoring force minus kx and minus bx dot. So B, of course, characterizes the strength of this damping force. Okay, so let's rewrite it quickly. So x double dot. Let's move to this side. Plus k over mx plus b over m. You know what? Let's write first b over m. I don't like. So let me write first b over m x dot plus k over m x equals to 0. Of course, who wants to drag tons of these constants? Let's just introduce new constants. So let's denote. Of course, first k over m, and now we're going to introduce omega naught squared, which is basically the same as omega over there, but now we have to be careful with this omegas because we're going to have eventually 3 omegas. So this is the natural frequency, angular frequency, right? Natural angular frequency when there are no damping forces. So the system would oscillate with this frequency when it is not exposed to any damping forces. So this is natural frequency. angular frequency. Right. Okay, and the second, let's introduce damping constant, but in this way, B over M equals to 2 times beta. You will see in a second. Okay, not in a second. Next class. Oi, we're already getting over time. So sorry. So beta is the, okay, let me write. Beta is the damping constant. Okay, let me frame this because these are important. Right. And so now let me write differential equation, and we will start from this point next class. So x double dot plus 2 beta x dot plus omega naught squared x equals to 0. Right. So, okay, so that is now our modified, changed differential equation, which needs to be solved. And again, we can say exactly the same words. Second order, linear, still homogeneous, no free terms. You see x agents everywhere, x dot, x double dot, so no free terms, homogeneous, and still differential equation with constant coefficient. So exactly the same words can be. Okay, so let's call it a day.